So guys, we were talking about the congruence rules, right, which actually just made us verify a few number of things among two triangles to actually make them conclude to be congruent. So the first congruence rule that we understood was the SAS Congruence Rule. What did this rule say? As the name suggests, you can see A is written in between two S. That means side, angle, side. Two sides and one included angle between the two sides is what this notation stands for. One side, another side, in between those two sides, the included angle between those two sides is the angle A representing. So this is nothing but included angle. According to the SAS congruence rule, you just need to show that what? Two triangles are congruent, it says, if and only if. What you need to verify? Only 3 equalities you need to develop out of the 6 equalities that we need in order to conclude that two triangles are congruent. SAS congruence rule reduces our argument to just verifying 3 equalities, because if these 3 equalities hold, automatically the rest of the 3 equalities also hold. We have the 6 equalities holding, the 3 related to sides, the 3 related to angles, and hence I can say that the two triangles are congruent. So what are the 3 equalities? It says that two triangles are congruent if and only if two sides and included angle, two sides and included angle of one triangle is equal to two sides and included angle, two sides and included angle of the other triangle. So you have to show that one side of one triangle is equal to some corresponding side of the other triangle, another side of one triangle is equal to another side of the other triangle, and the angle between them are also equal. Is it understood? A very beautiful application of the SAS congruence rule is this result, which says that angles opposite, it says angles opposite to equal sides, angles opposite to equal sides are equal. Angles opposite to equal sides are equal. For example, you have a triangle in which two sides are of same length. Say this is my triangle ABC. These two sides are of same length. Basically, this is an isosceles triangle, right? In a triangle in which two sides are of same length is said to be isosceles. All 3 of different lengths is said to be scalene. All 3 of same lengths is said to be equilateral. So right now I am talking about isosceles triangle. If these two sides are equal, then the angles opposite to them should also be equal. I am talking about these two angles. So angle B should be equal to angle C if side AB is equal to side AC. So if I am saying let AB be equal to AC, then I have to show angle B is equal to angle C. If this is shown by me, the conclusion would be that if two sides are same, then the angles opposite to them are also same in measure. Clear? I have to show angle B is equal to angle C. In order to develop this conclusion, as I am saying, it's a application of SAS congruence rule. SAS congruence rule is used to develop the very conclusion for two triangles being congruent. Right now I cannot see two triangles being congruent. So how can I say SAS congruence rule will be used over here in order to prove these two angles are equal? I somehow construct a particular line in here to develop two triangles. So what I do, I consider the angle bisector of angle A and make it meet the opposite side of angle A, that is BC, at D. If AD is the angle bisector of angle A, so I am saying construct, I am constructing, okay, construct AD, or I should say construct angle bisector of angle A and make it meet the opposite side, that is BC, at D. So if AD is bisecting angle A into two equal halves, that means this angle is half of angle A, this angle is half of angle A. So if I am saying this is angle 1 and this is angle 2, from here I know this implies angle 1 is half of angle A and angle 2 is half of angle A. That is, angle 1 and angle 2 both are equal to half of angle A. Why did I construct this angle bisector? So that I can get two full-fledged triangles. One is this triangle you can see, other is triangle ACD you can see. If I separately draw these two triangles, you know what I am interested in? I am interested in proving that these two are congruent, right? If I separately draw these two triangles, I have A here, B here, D here, again A here, D here, C here. Somehow I need to show these two triangles are congruent. I am interested in using the SAS congruence rule. If I show one side of this triangle is equal to one side of this triangle, another side of this triangle is equal to some other side of this triangle, and the included angle here between those two sides is equal to the included angle here between the corresponding two sides, then by SAS congruence rule, both of them will be congruent. Can you see any two sides which are equal in the two triangles? Yes, of course, AD is equal to AD. Right? The same side is being used in this triangle also, in this triangle also. So clearly, this is the common side. So of course, it will be equal. First thing understood? After that, I am already given that this is an isosceles triangle. So AB is equal to AC. So also AB is equal to AC, that is given to me. So two sides of this triangle are equal to two sides of this triangle. Right, and I have understood the corresponding sides also. This gives me some correspondence between sides. I know that AD side is corresponding to AD side, AB side is corresponding to AC side. Right, among the two triangles, the correspondence between sides we are also simultaneously developing from these equalities. Now, just if I show that the included angle between these two sides in this triangle is equal to included angle between these two sides in this triangle, by SAS congruence rule, these two triangles will be congruent. What is this angle BAD? Angle BAD is nothing but angle 1 and this angle is angle 2. I know that angle 1 is equal to angle 2 because AD was actually the angle bisector of angle A, and therefore this is half of angle A, this is half of angle A. So in measure they both are equal. So I have angle BAD is equal to angle CAD. So if this is true related to these things, I know this side is equal to this side is equal to this side, included angles are same. So by SAS congruence rule, so I'll say AB is equal to AC, AD is equal to AD, angle BAD is equal to angle CAD. Therefore, by SAS congruence rule, this triangle is congruent to this triangle. On what basis I will be writing the symbolic form? For that I need the correspondence between vertices, which will be given to me from this fashion. Clearly you can see, very easily you can see AD is corresponding to AD. That means when this triangle will be superimposed over this triangle, AD side will be covering the AD side. For AD side to be covering AD side, A should fall over A, D should fall over D. So automatically C should be made to fall over B. You are left with one vertex that will be associated with this one, right? That is the case. So by just understanding the things that you already have, because AB was equal to AC, you know that these two are corresponding sides. AD was equal to AD, so these are corresponding sides, these are corresponding angles, right? One pair of corresponding angles, and from here only you can develop the correspondence between vertices, which is actually leading you to get the two triangles congruent, and from there you can infer the symbolic form of writing that the two triangles are congruent. So I have understood, this gave me the hint that AD will cover AD when one triangle will be superimposed over the other. For AD to cover AD, A should fall over A, D should fall over D, and therefore C should fall over B. So from here I have this correspondence between vertices, and B is corresponding to C. If with this correspondence between vertices I superimpose one triangle over the other, I will be getting them to be exactly covering each other because they are coming out to be congruent. Okay, so I write triangle ADB is congruent to triangle ADC. So you know that two triangles are congruent, but to write that symbolically, you should be aware about the correspondence between vertices, which is giving you that fashion of superimposition of one triangle over the other, which is going to make it exactly cover that one. And this is that, which was very, very easy to develop. You have these equalities with you, pick up any one that is going to give you a correspondence between the sides or between the angles, and that is going to help you get the correspondence between vertices. Let's tackle a question. See in here, if I have got this, has my result got completed? No. If these two triangles are congruent, that means when you are superimposing this over the other, it is exactly covering it. That can only happen if corresponding sides are equal and corresponding angles are equal. With this fashion of writing the congruence, I know, or with this fashion of correspondence between vertices, either of the two you can use, you can get the corresponding sides and corresponding angles. What are the corresponding sides? AD is corresponding to AD, DB is corresponding to DC, and AB is corresponding to AC. And what are corresponding angles? Angle A here means BAD, and angle A here means CAD. Then angle D. Angle D is corresponding to angle D. So here it is ADB, and here it is ADC. Then you have BC, so here it is angle ABD, and here it is angle ACD. So from this correspondence between vertices, I have got the corresponding sides and corresponding angles. If with this correspondence between vertices I am getting the two triangles being congruent, that can only happen if corresponding sides are equal and corresponding angles are equal. So this will be equal if these two triangles are congruent, and this will also be equal. From all these equalities which are coming up as a result of two triangles being congruent, I am only going to need one equality, which is this. All these I don't require. I am getting this. I am happy. Why? Because this is proving that this angle is same as this angle. And that was what I wanted to show. I wanted to show angle B is equal to angle C, that is angle ABD is equal to angle ACD, and that is what I have got as a result of these two triangles being congruent. So there was an artificial construction made in order to, what? In order to get two triangles and then use SAS congruence rule in order to make them congruent, as a result of which I got two angles equal. So I have proved that if two sides are equal in a triangle, then the angles opposite to them will also be equal. After this result, let's talk about a small easy peasy question. The question says, this is the triangle, I am extending this side deliberately. This angle is 120 degrees. this is A, this is B, this is C, and say this is D. You are given that these two sides are equal. So you are given AB is equal to AC. Question is, find angle A. What is the approach do you think you can use over here? AB is given to be equal to AC. We just now did that angles opposite to equal sides are equal. So you have with you this angle will be equal to this angle. So I will have AB equal to AC, implying that angle ABC is equal to angle ACB. That is what? If angle B is equal to angle C, if this is x degrees, even this is x degrees, right? That is equal to x degrees. Now if I talk about this segment, if you can clearly identify, this is like a ray standing on a straight line, thereby the two adjacent angles formed will form a linear pair of angles. So I will have what? X plus 120 equal to 180. X plus 120 is equal to 180. They are forming a linear pair of angles. So x will be equal to 180 minus 120, which is 60 degrees. You have got the measure of angle C as 60 degrees, but angle C is same as angle B, so even angle B will be 60 degrees, which is angle ABC, angle ACB. Both are equal because of the fact that angles opposite to equal sides are equal. The moment you are aware about two angles in a triangle, can't you be aware about the third angle? It is very, very simple. Angle A plus angle B plus angle C is 180. I am talking about internal angles, not exterior angle at angle C, but internal angle at angle C, interior one. So angle A plus angle B is 60, angle C is 60, is 180. This is 120, 180 minus 120 is again 60. So angle A is again 60. Fine, this is again 60. In fact, if this is a triangle with all interior angles equals to 60 degrees, this is an equilateral triangle. Not just these two sides, but actually this third side also will be equal. All of these three sides will be equal to each other, because in an equilateral triangle only, you have all the three angles of 60 degrees each. So if these two sides are equal and all the three angles are coming out to be 60 degrees, third side will also be equal to the two sides. So all the three sides will be equal to each other. You will have this to be an equilateral triangle. After the SAS congruence rule comes the next congruence rule. Now see, every time it doesn't happen that you get two sides of one triangle equal to two sides of the other triangle and the included angle between them also equal. All the time this ideal situation does not occur. So I need another shortcut to actually allow me to just verify a few things between the two triangles and conclude that they both are congruent, and hence all the 6 equalities are going to hold thereon. So we have this next congruence rule after SAS congruence rule, which is ASA congruence rule, exact opposite to the SAS congruence rule. Obviously A stands for angle, S stands for side, again A stands for angle. If two angles of one triangle are equal to two angles of the other triangle and the included side between them is also equal, you say the two triangles are congruent by ASA congruence rule. Okay, there it was two sides equal and included angle equal. Here it is two angles equal and included side equal. So the thing sitting in between is actually representing the inclusion of this side between the two angles. That is why S is written between the two A's. You cannot change the name. This is ASA. Two angles and one included side in between the two angles. So what does it say? It says that two triangles are congruent if and only if. Two triangles are congruent if and only if two angles and one included side two angles and included side of one triangle is equal to two angles and included side of the other triangle. Okay? I have to prove this now. The SAS congruence rule, there were no grounds for us to actually prove it in an analytical fashion, but now we have SAS congruence rule established with us. Based upon that, using that, we will be proving the ASA congruence rule. So let's begin the proof. Fine. I have to show that if two angles in one triangle and included side is equal to two angles in the other triangle and included side, then both the triangles will have to be congruent. So let's consider two triangles which we are interested in proving to be congruent. Say this is A, B, C, D, E, F. Suppose this angle is equal to this angle is equal to this angle, and this included sides are equal. So this is given to me. Angle B is equal to angle E, angle C is equal to angle F, two angles are equal, and included side is equal. With this given information, can you show that when this triangle will be superimposed over this, it will exactly cover it? That means, can you show that two triangles, triangle A, B, C, D, E, F, they are congruent? Now this proof involves three cases. Either this side AB will be exactly equal to this side DE, or the length of side AB will be less than length of side DE, or the length of side AB will be greater than length of side DE. On the basis of length of these two sides, comparison of lengths of these two sides, I will be concluding in three cases the congruence between these two triangles with these given conditions. So let's take case 1. When this length is equal to this length, AB is equal to DE. The moment AB is equal to DE, this angle B is already equal to angle E, and BC is already given to be equal to EF. I will have two sides of equal length in these two triangles and one included angle of equal measure. So therefore, by SAS congruence rule, these two triangles will be congruent. So if AB is equals to DE, also angle B is equal to angle E and BC is equal to EF. This is already given to me. So you have two sides of one triangle equal to two sides of the other triangle and one included angle same. Therefore, by SAS congruence rule, you get this triangle is congruent to this triangle. In what fashion I will write it symbolically? See, AB is equal to DE, that means AB side is corresponding to DE side. Fine. That means when this triangle will be superimposed over this, DE side will be falling over AB side. DE side will be falling over AB side. That means for that D will have to fall over A, E will have to fall over B. So D will have to fall over A, E will have to fall over B. So the left out vertex will have to fall over the left out vertex, that is F will have to fall over C. F will have to fall over C. This is how I develop the correspondence between vertices by the given conditions to me. So you would have also said BC is equal to EF. For BC to be equal to EF, BC should completely cover EF, right? So B should fall over E, C should fall over F. So B should be related to E and C should be related to F. So you are left out with A and D, so this is how they should be related, right? So with this also you can develop the correspondence between vertices, or with this also you can develop the correspondence between vertices. I only need these correspondence to write in symbolic form this triangle is congruent to this triangle. So I will have triangle DEF is congruent to triangle ABC, or triangle ABC is congruent to triangle DEF. In any way you can write. This is congruent to this is congruent to this, any way you can write. Fine. Now comes the second case. When length of AB is not equal to length of DE. So let me rub this. Length of AB is not equal to length of DE. Fine, that's case 2. Length of AB is not equal to length of DE. That gives rise to two situations. If I am saying AB is not equal to DE, either AB's length is less than DE's length, or AB's length is greater than DE's length. We are going to discuss this in case 2, and we are going to discuss this in case 3. Try to focus upon this situation and see if DE has length more than AB, how can then also I prove that both these are congruent, given that these two angles are equal and the included sides are equal. Try to think upon it. We'll be completing its proof and watching out its applications in the next lecture. So I'll see you then. Thank you.